things, and we worked on that. Then you came back after that and you applied, you took out one of your members. You will take this one out of here, and we erase this piece here. We'll just erase the rest of that. And we put a rubber band in. I'm going to draw the rubber band in as red, and to show that that was the rubber band. And the rubber band came in between here and completed the third side of our triangle. Then you applied your forces again, and we're going to come back in. We're going to show our force coming in again, and we applied a vertical force and a lateral force to it. And as you applied a vertical force down, you're going to push. It's going to push down, and you're going to see the ends of this try to squeeze outward here. So you can see that what you're seeing is as you apply a vertical force to this member, this piece here undergoes tension. The top is undergoing compression. It's pushing down and squeezing, yet this part is under tension because it's pulling apart. Okay, while we're using the rubber band to simulate this third member right here, and we apply a downward force, we feel some resistance to it, but not a lot because the band's very elastic. When you had the Connex rod in there was a lot of resistance to it. The Connex rods are not very elastic, and they give a lot of resistance back. And this kind of leads us to the next part of this, where you get an equilibrium in forces. So your total downward external force that you apply is equal to the total internal reaction force in the opposite direction. So you can come back, if we come back and look at this, what goes into it, right here in your downward force, comes back out in this external force, but in the other direction. It's pushing out away from everything. So this is coming straight down, and this is pushing out away, and these forces are equal. These will equal out and put everything into equilibrium. Pretty self-explanatory. It goes back to law of conservation. Now though, when we look at it, and we're going to come in, we can look at the rubber bands. You can look at it in other ways. If you wanted to actually replace the rubber band and turn it sideways, so you have, here's your two sides, and then we put the rubber band here, you get the same effect. Now, if you do that, make sure that there's some tension in the rubber band. But as you apply a downward force here, you're going to feel it squeeze, and it kind of acts as a hinge. Again, it's that same resistance to movement and that same reaction to the forces being applied in the opposite directions is what we're seeing in that. Now, we moved into the third activity, and we went in and you created an actual structure out of several triangles, and we're going to look at some of the same effects in the next. Alright, in part 2 of our activity, we went in and we made a little truss structure. This is called a truss. It's actually just a connection of several triangles put together, inverted with each other, and you make one solid structure out of it. And when you go in and you apply your downward force to it, and you apply a downward force on it right here, you see that it's very, very strong, and it's hard to distort it. It's a lot harder than it was even with a single triangle. And if you come in here and apply a lateral force to it, you get the same thing. It's extremely hard to displace it and move things and make it move out of shape. Now we can simulate that again, and what I want you to do is we're going to go in, and I'm going to change this up just a second, and we're going to apply a red line here. And what I want you to do is take out this beam right here, and I want you to take out this beam right here, and we're going to replace those with rubber bands, and again apply your lateral and your vertical forces to it, and you can see that again the forces move out and around, and that everything helps support each other, and you get a very strong structure out of that. As you can see in this diagram, I've shown where the different forces come in and apply, and where we have tension and compression. Now we're going to apply a downward force right here on the lower chord. Again, this is your lower chord right here, and then up here is your upper chord. So we're going to apply a downward force onto our lower chord, and we'll see that as we push down here into here, this is going to push these parts of the beams away. So right here we're under tension now because you can see the arrows are pushing away. We can also see that we have an upward force. This is called your normal force, and this is what the tabletop is pushing up onto the bridge or wherever the edges of the bridge is supported, because this is your open area. So we have tension here. We end up with tension here as these beams try to pull apart, but we end up with compression. This part here and this part here both try to come together, and this also comes together, and this is what makes this truss structure so strong, is that even though this is under compression, everything else on the outside is under tension, and it forces itself together and distributes the weight outwards for you. So I want you to go in and we experimented with rubber bands in different places so that you could see all of these parts coming together, and then we looked at it and watched what all happened. Now we're going to come in. You saw what would make the longest beam, and then you also saw if you could make some other shapes and other structures and what would give you other strong structures that you could work with and to get nice firm construction. So does making the beam thicker have any disadvantages when you're building a bridge? Things that may come up are adding weight, adding cost. Those are all huge and costly to the builder and to the engineer. But you can, if you look through this truss structure, we can actually add strength and rigidity without adding